Okay, so today we'll look at circuit design techniques for very low voltages. So what are the major circuit building blocks in any chip? You have the logic cells, then you have circuit related to clocking, which essentially the main elements are the latches and flops, and for clocking then you have the buffers, which are just standard inverters. Then there's also the clocking methodology, synchronous versus asynchronous, and a very important element of clock design is the clock network, which distributes the clock from the clock source, which is a PLL or DLL or whatever it is, to the rest of to all the sequencing elements. And the clock source itself, the clock reference, there will be some crystal of some kind which will get multiplied, so the PLL, so that circuitry is also another very important component. Question?
So, last class, Indian using a minimum energy point tracking system we discussed in the class. So,
We'll discuss that after this. Okay, so we'll first look at the circuits for building blocks and then we'll look into that. What is the other important element in any digital chip? Memory, right? So memory is another component which we have to figure out how to make it work at very low voltages. And then in any mixed signal SoC, you have analog and RF components, and also non-volatile memory is very important for many applications, standalone applications, IOs, and then test infrastructure, built-in test. So we won't, of course, be going through all of these. Definitely not the analog RF and non-volatile memory in this course, but any SoC, if you want to build and make it low power, you have to kind of keep that in mind, including the IOs. So first, let's look at one very important sizing related aspect, which has an influence on the kind of variations you see in the transistor's threshold voltage. Because if you recall from the last class, it's the variations in the threshold voltage which kind of limit how low a voltage you can scale from a practical perspective, right? It kind of it basically prevents you from scaling too low. And these are variations which are global. What we mean by global variations are variations where all the transistors in the chip, the threshold voltage changes in a correlated fashion. So you have what are called the slow, fast, and typical process corners, and there is a shift of the threshold voltage in a correlated fashion of all the transistors, one way or the other. Local variations are also known as within die variations within the same chip, based on different locations. At different locations, the transistors will have different threshold voltages. So the threshold voltage is also a random variable which has two components.
global is for across the wafer.
Global is across the wafer as well as across wafers, because you have exactly, it's a die to die variation and you have within die variation. So you can break up the variations into two components, die to die and within die. And also, of course, you have changes in threshold due to temperature. So if you want to kind of come back and control the threshold voltage, you have to look at what are all the factors which determine the threshold voltage of a transistor, right? And as a circuit designer, what are the things you can do? So you look at the threshold voltage of a transistor, the body doping, the channel length, the channel width, and the body bias. These are the various things which have an influence on the threshold voltage. Now, doping is something which happens one time during the fabrication process. But as a designer, you have a choice as to which threshold voltage to choose, right? Because any process now comes with transistors with multiple different threshold voltages. So it's a one time, during design time, you identify what is the threshold voltage to use, and then you pick that in your design. But once you make the design, okay, then you have also another choice, which is the sizing. Based on the sizing, you can decide, you can also control the threshold voltage. Ideally, it should not have happened, but the fact of the matter is that you have impact of the channel length on the threshold voltage. You have short channel effect, you have reverse short channel effects, narrow width effects, reverse narrow width effects. So you have to be aware of what are the non-idealities, and actually you might be able to take advantage of this in the design of your, in the sizing of your transistors. Finally, the body bias control is the electrical control. You can, if you can control the body voltage, you can modulate the threshold voltage with that control. Now it turns out that the effect of body on the channel, in fact you don't want the body, ideally for a transistor operation, you don't want the body to affect the channel's threshold voltage, because if it does, then it leads to the gate loses control of the channel, and the behavior of the transistor, instead of being a square law device, it becomes velocity saturated, and you don't have a good behavior of the transistor. So, and also as we scale down the transistors in deep submicron, the impact of the body is becoming less, and also certain process flavors, body is not even available to you to control, right? So FinFETs and so on. So as a technique for deep submicron nodes, using the body node as a way to control the transistors parameters is not a very scalable approach or sustainable approach, right? So you have to look at other ways of controlling the threshold voltage. One interesting approach to control the threshold voltage is to use the channel length, and instead of using the minimum channel length, you can use longer channel lengths. And what that does is, we'll see in the next slide some work done by these researchers where they have studied the impact of the channel length and see how that helps to reduce the variations as well as the leakage. So increasing the channel length, of course, what it does is, whenever you increase the channel length or the channel width or the product of the two, the area goes up, and as the area grows up, the variations does come down. But there is you see again, there is you have to kind of do it in a careful way, because if you increase the area, variations come down, but the area goes up, so the capacitance goes up, so the dynamic energy can go up. So you have to kind of do it in a very careful, calibrated way. So and the other problem of increasing the channel length is your speed will come down, because the whole point of scaling is to reduce the channel length and get speed, but by increasing the channel length, you are kind of compromising on the speed. Now, when you have paths which are not critical in terms of speed, you can definitely do this. And also for sub-threshold, near-threshold computing, where we have anyway targeting not very high performance, right? Kind of low to medium performance devices. Increasing the channel length might be a good strategy. So this graph is taken from this paper by David Bohl, which we have, it's one of the papers for you to read up. And what the author does is, he shows the impact of channel length scaling on the noise margin of two back-to-back gates. Remember in the last class we said, if you want to, one quantitative way of studying the noise margin is to take the two gates and cross-couple them, put the output of one as the input of the other. And then you get the noise margin by doing the DC transfer curve. And then you get a butterfly diagram, and you look at the size of the largest square which you can embed there. So what is being plotted on the x-axis is the size of that square for two different voltages, 0.4 and 0.3 volts. And what the author has done is, he has done a Monte Carlo analysis so that you have a statistical distribution of the noise margin values. And that is being plotted here as a histogram also. So clearly when you reduce the supply voltage, the noise margin comes down, because everything has shrunk. So that is why the graph from here shifts here. And then there is a spread, and that spread comes down a little bit when you go from the gate length, the drawn gate length of 40 nanometer to drawn gate length of 60 nanometer. It has tightened up a little bit. It may not be very easily visible to a naked eye, but it has actually tightened a little bit. Kind of basically saying that the spread has been reduced by increasing the channel. So this is something for you to keep in mind even for your project as you're thinking about the project and how to size it. So this gives you a kind of a way as to what this person has done, and you can also try it out and see how that works out for you. So now besides sizing, another important consideration is related to the fanon of logic cell. Typically what happens is that when you have you know that as an AND2 gate or an OR2 gate is a universal logic gate. Right? That is enough for you to build any Boolean function, and you can build any digital circuit using just an AND2 gate. But it turns out that it might not be a very efficient way just to use NAND2 gates in terms of area, right, and speed and so on. There is a case to be made for more complex gates. Right? You can always cascade a bunch of NAND2 gates to get a more complex Boolean function. But you can build a monolithic Boolean function by taking the Boolean function and creating the switching network for the pull down and the pull up in the same gate. Right? So that is a monolithic gate. When you do that, what happens is that the area occupied by the gate becomes smaller, and you can also get some benefits of speed as long as the number of inputs is reasonable. So that is why you find in the standard cell libraries that you have a variety of gates. Right? You might have hundreds of logic cells and with some large number of inputs and complex Boolean functions implemented in the same gate. Now, so that is the benefit, and that's why you have these, so that when the synthesis tool synthesizes your RTL to that, you can have a compact implementation of that with a small area. Because area is money, so you want to always keep the area small. And that is what is typically done for super threshold operation. Now, when you come to sub threshold operation, you have this problem that the off to on currents are not too different. In the super threshold, you can have at least 1,000 times difference between the on to off current. Whereas in the sub threshold, even your on transistor is operating in sub threshold, and off is also sub threshold, right? So they are kind of comparable in some sense. They'll be off by a factor of 100, or but due to variations it can come down. So now what happens is that, say you have a large fanon gate. Right? You have a complex gate with a large fanon. When you have a large fanon, what does it mean? You know that one of the pull up or the pull down will have series, the other one will have parallel. Right? You will end up with that kind of a situation. There will be, of course, very few gates where it's what are called symmetric gates, where it's the same for both pull up and pull down. But most of the other Boolean functions, it's you can have series you'll have series in one which will translate to parallel in the other stack. So when you have that, you have this problem where you have, let us say you take this 3 input NAND gate, you have an on current for the pull down, but the pull ups are supposed to be off, because let's say all the 3 inputs are high, but all the pull up currents are adding in parallel. The off currents are adding in parallel, and then you have one single on current which is down. And the off and on currents are not too far off because VDD is in the near threshold or sub threshold. And you can end up where this doesn't work properly. Right? This you can also relate to the imbalance factor. So this is a problem where you have large fanons, you have large imbalances, and your logic levels get compromised. You don't have a proper logic 0 in this case, or conversely you can have an improper logic 1. So the noise margin gets compromised.
If I connect the PMOS, that connected PMOS below the that will limit the.
So the question, the point being raised is, why not limit the pull-up current by putting a diode connected PMOS? Okay. Now, of course, you can play that game. In fact, that is what is done, if you remember, in the level converter. In the level converter, the current in the PMOS was reduced by putting a diode connected PMOS. So you can do all those games, but the thing is that you have to kind of carefully engineer some of those things. It's much better to basically say that, look, I'm not going to have too much of an imbalance, and you are so what is done is that standard cell libraries for sub threshold and near threshold, you prune the library and remove cells which have very large fanons. That way, you keep a fanon of 3 or less. so that you don't have too much of this imbalance. So the question is, if I were to put a diode connected PMOS to limit the current, right? So what will happen? So maybe we should look into that a little bit more. So let us say we put a diode connected PMOS here. So firstly, what do? We put a diode connected NMOS or PMOS. So if you put a diode connected NMOS, then the pull-up will degrade the time required of pull-up will degrade very rapidly, because as the circuit is pulling up, the gate source voltage will start reducing and the current will start dying exponentially, right? So you will have a problem with the pull-up speed. If you put a PMOS diode, so really what you have done is then you have kind of effectively reduced the supply voltage and you have put a series resistance again, right? So, so that does help the imbalance issue, but it will also affect your speed, pull-up speed. So it's basically, it's not, it might be okay for certain cases perhaps. You have to look at it in a case-by-case basis, where you really want a very high fan-in structure, but you don't want to have this problem. So perhaps you could think of limiting the pull-up currents and trying to solve this particular imbalance problem. So what people do is avoid large fan-in gates in the standard cells used for the sub-threshold operation. The same thing also happens for muxes. Many places you have a mux structure, and if you think of a mux now, let us say one path is activated, right, and the other paths are off. Then you can have leakage in these other paths. So you can have an on current going like this, but you can have off currents, and because of that, again you can have an improper operation of the mux. Again, this is happening because the currents, the on and off currents are not too different. So you have to pay attention to these kinds of issues. So again, you limit wide fan-in muxes, or maybe change the structure of the mux. Don't allow for this kind of pass gate type mux. Go for a tri-state inverter type mux. The reason you like to use pass gate type mux, what is the reason you think this mux is used for high voltages, super threshold operation, as opposed to tri-state inverter type mux? See, the reason this is a nice mux to use, if possible, is that NMOS and PMOS both are in parallel, right? So both help each other. So the speed is much better if I use this mux. Whereas if I use a tri-state inverter, what is a tri-state inverter? Imagine this mux, there is one simple inverter driving this. Other way of doing the mux is push this PMOS put it in series with the PMOS of the inverter, put the NMOS in series with the NMOS of the inverter. So you have a series PMOS and series NMOS. There, the speed of that will be lower than this, right? Because in a pull-up, only one PMOS of the mux is coming in, and pull down only one NMOS. Here, in this structure, both are there in parallel. So that's why you would prefer this. But then, if you use this, you have a problem with the sub-threshold operation, because if you have too much of a fan-in, you can end up with a issue that it will not work properly. So again, you limit the fan-in for this muxes. So really what we are saying is have as low a fan-in as possible, 3 or less, and you have to pay particular attention to pass gates. Any logic cells which have pass gates, you have to be very careful and really analyze the leakage currents. Typically when we have pass gates, see in CMOS and in digital circuit, we always assume signal is going in one direction. But with a pass gate, you have signal can flow in either direction. And you have to really watch out and see if it goes in the other direction, will it be a problem? Okay, and especially during the off state of a mux, if signal can go in the other direction, you can end up with a big problem. So, for example, in this paper by Intel, which I put a link on our class website, so you can read up this paper. So what they do is they look at the latch, standard register, right, which is a master slave flip flop, master latch and the slave latch. And what is a latch? Latch is basically two back-to-back inverters. Then there is a mux. There is a transmission in a standard latch, super threshold latch. There would have been a transmission gate here and here, and then you would have either a tri-state inverter or another transmission gate. So what these people do is they remove this, instead of putting a transmission gate here, they use a tri-state inverter. This way, what happens is that they say the clocked inverter prevents a write back. So you have master and slave, and this is supposed to be off, but you can have leakage back from here if you were to use a pass gate. So that is where, again, because we are talking of situations where voltages are so low that even an off leakage is comparable to an on current, right? Because everyone is operating in subthreshold, so you have to be careful about that. So this allows you to keep it unidirectional. So you want to have write back from the output to the input. So clock network design. Now one of the key problems in subthreshold is the hold timing problem, hold timing violation. Typically you have both setup violation and hold violation, right? Both you have to worry about, max timing and min time. The thing is, we are talking of, when you use the subthreshold, anyway, the voltage, what is the supply voltage to use, right? It's a little fuzzy concept, right? Especially if you put in your feedback loop and have adaptive voltage scaling, etc., etc., supply voltage can be adjusted. So whenever you have a setup time violation, you increase the supply voltage a little bit and it will be okay again, right? Max timing will be taken care of. So with all your feedback loop or whatever it is, you can easily take care of the max timing problem by adjusting the supply voltage. But min timing, what is min timing? Min timing is I have a source flop and a destination flop. The source flop launches the data in a particular clock edge. The destination flop is supposed to capture the data in the following clock edge. But if the path is very fast between the source and the destination, and there is a clock skew in the destination flop's capture, this data of the same cycle can get captured in that edge. Right? That is the problem. You cannot really fix the problem by adjusting voltage or anything. That's the end of the chip. Okay, so the hold time is a big problem, and the hold time is coming because the biggest source for the hold time violation is the clock skew, and the clock network itself will basically, because of the variations in the threshold voltages of all the buffers in the clock tree, there will be quite a bit of skew between the clock edges which come to various latches and flops. So that is a big problem which you have to deal with. So what is done is, what is proposed is, what is basically use a shallow tree. Shallow tree means they are not using too much depth in this tree. Secondly, they use the final stage of the tree is a metal grid which is shorter. So all the flip-flops and latches are feeding off this particular metal grid. They are, this covers the entire IP which is running off this low voltage, and all the flops and latches are just feeding off that. The idea here is that the metal RC delay is almost negligible in the subthreshold regions because we are really operating at speeds of few megahertz, right? 10s, 20, 100 maybe. Even that is a small speed compared to the modern processor speeds. So the RC delay the wire delay is small. So the skew due to wiring is small. So you can think of this as instantaneously the entire grid is going up and down. So when you do it this way, the entire grid goes up and down. So this relative skew is very small. Okay. So you might have, if you had not shorted this, the arrival time of the edges could be different out here. But because you have shorted it like this, the effectively the clock grid goes up and down at an average timing based on all of this. On an average, it does in some sense an averaging of the arrival time of all of this, and the entire clock grid goes up and down based on that. So this is the approach Intel guys have taken for their low voltage chip. Okay, so the question which is being asked is, can we have a situation where the final buffers are fighting with each other? That is, one is trying to pull up, the other is trying to pull down. Now, if you had this kind of a scheme where the buffers were being driven by signals which you had no control over, and then that could happen, and you don't want that to happen. But you see, these are all buffers driven from the same clock. So it's like, think of it as one big buffer, giant buffer, which is implemented as bunch of parallel inverters. Bunch of inverters which have been just spread out. Right? Anytime you want to build a wide transistor, you don't build one single transistor with a very wide, very large width. Right? You make it up in terms of small width transistors with number of them in parallel. That's basically what is happening here. Right? A number of these are in parallel, except they're spatially also spread out.
There can be delay between the buffers. So can't it be jitters on both?
No. Okay, so the question is, if you have different delays coming in out here, what will happen to the output? Correct. The arrival time difference could happen due to maybe different propagation delays and different delays of these individual buffers. Right? That's what leads to clock skew. The thing is, the clock skew hopefully is still a small number. Right? It's still maybe at most 1 gate delay across these. So when you have, it won't be too large a clock. It won't be like they'll be off by, multiples of gates. They'll all be within a gate or a fraction of a gate delay. And when you have these signals which are off by a fraction of a gate delay, and when you short them, the output edge will actually be a degraded edge, but it will be in between the two edges. Imagine that you have two inverters which are giving an output which is off by a small number. Okay, which that difference in delay is maybe say 1 gate delay. When you short the two outputs, the output now will actually, in some sense, what is called interpolate. The actual edge will be interpolated between the two edges. And in fact, that is a technique which is actually used to generate edges with fine control. Actually, you can take two buffers, you can short the output, and by controlling the delay of each of them, you can position the output edge. You can control where the output edge happens. So that is a technique which is actually used to control the timing of edges in various circuitry like PLLs, clock and data recovery circuits and so on.
So at very high frequency, this will be a limitation. Like if the gate delay becomes comparable with the RC delay of metal nanos, then perhaps we cannot use this technique.
So the question is, if the RC delay becomes comparable with the gate delay, what will happen to this, right? The thing is that, yes, so the RC delay has to be kept small. Now the problem comes because of that at high voltage, at super threshold operation at high voltages, the RC delay and the gate delays become comparable, right? Unless you size the wires to be wide enough such that the RC delay is a small fraction of the gate delay. And how do you size it? You increase the width of the wire. When you increase the width, the capacitance goes up. So the power consumption of this approach really goes up at higher voltages, but you do get very low skew. If you want the lowest skew clock network, this is the approach you should take. And this was the approach which was used in the first high performance microprocessor which was developed in the early 90s by DEC, the alpha processor. So the alpha processor had reached a speed of 200 or so megahertz. At that time, now it looks ridiculously slow, but that was like a breakthrough speed because all the processors were 40, 50 megahertz and they crossed the 200 megahertz barrier. And they used a clock network like this, which was like a grid, but the whole clock network consumed 50-60% of the total chip power just to deliver the clock, because you have a lot of capacitance like this. So people moved away from this way of designing clock networks for the processors, and you have more of a clock tree and fine tuning of the clocks, such that you still get low skew but lower power. So now when you come back to this particular design, which is giving you a low skew for the low voltage, maybe the clock power might not be that much of an issue at this sub-threshold. But if I want to make the same chip operate even at high voltages, then you see you have a is this the right way to do it, right? How do I design a chip where it can work well at low voltages as well as at high voltages? Maybe it is not optimized for the highest voltage, but it's not also too bad. So that is definitely a challenge as to how to do it. So that's not clear yet. Now another thing which the Intel people also did, and was to actually have these programmable delay blocks, so that they can tune the delays, so that the skew between this portion and this portion can be adjusted. Also, you see out here that they have this level shifters, because the memory, they are not adjusting the supply voltage of the memory as much as for the logic. So they have three domains: a VCC for the clock generator, which is the phase lock loop, which is kept fixed; the logic VCC, which is adjusted all the way down to a couple of 100 millivolts, and the memory VCC, which also comes down but not as much as the logic. So the programmable delay elements basically allow them to compensate for skews out here. Of course, you need a way of measuring the skew so that you can figure out how to compensate by. That is not discussed here in the paper, but there are there are other papers where people have discussed how you can measure the skew, and then once you know what the skew is, you can maybe go and adjust and try to get the skew down to 0. And how to build the programmable delay element itself. Any thoughts on that? What exactly? So you look at what determines the delay. Delay is effectively an RC product, right? Resistance, effective drive resistance of the gate and the capacitor. So you have to adjust one or the other or both. That way you can adjust delay. So one way is to have a bank of capacitors which are controlled by a switch, and you decide how many to turn on or off. That way you can digitally adjust the delay. Similarly, you can have in your driver multiple parallel paths for pull up or pull down, and you activate one or more of them to adjust the drive strength and hence the delay. So you can have a digital control. You can also have analog control, where the pull up or pull down or even the capacitance value can be controlled by an analog voltage, so that you have an analog control of that.
You can have the delay synthesizer of
Correct. So the suggestion is, why not also use a delay synthesizer? Now the thing with the delay synthesizer of the paper from Nakai is that basically what the synthesizer was essentially is a bunch of logic gates, bunch of wire segments, and then you have a mux to select the two. Now the question is, at what resolution can you synthesize the delay? If you have a bunch of logic gates and you select between 1 stage versus 2 stage versus 3 stage, your delay resolution is in the amount of logic, in steps of logic cells delay. Whereas in the clock skew, maybe you want to compensate fractions of delay. So that might not be a good approach to do that. But you can use the same, as I said, you can have two paths, one path having 2 logic cells, another path having 1 logic cell, and both the paths are shorted, and you can control the weight between the two in some sense, kind of like this mixing what we are doing out here to adjust the delay between. So there are many different topologies for adjusting the delay, and also to adjust delays at sub logic cell delay resolution.
So these adjustments are going on in runtime. We are adjusting in runtime. So if there is a queue, it will take some time to adjust this queue, adjust the delay. In that time, the same malfunction. There is a queue.
So the question which is being asked is, how are these adjustments made? Are they always happening during runtime? And if it's not well during the post time when it's not properly adjusted with large skew, can there be a problem? Now these, I don't remember whether this authors of this paper have discussed what they did out here, but I would imagine that they are doing it once during chip bring up. In the beginning, you do set it, and that's it. You don't keep adjusting it during the lifetime of the chip. Okay.
Changing voltage and temperature, it may change.
It may change, yeah. So when that happens, if that is a large change, then you have to keep adjusting it uh, for the continuously, right? You have to have a feedback loop which keeps adjusting it continuously. So in the beginning, you let it go. You don't have any operations. Let it adjust and get to a point where skew is very small, and then you let it run. So the feedback system is continuously monitoring the skew. So if the skew goes beyond a certain value, it will go and adjust it to bring it back. All the time ensuring that it never goes beyond a threshold, a value which will cause a malfunction. Now the other thing also, what you can do for these very low power chips is look at the microarchitecture. The chip. How do you how many pipe stages are there? I mean, you have a piece of function you want to compute. How many copies of the function do you have so that you do things in parallel, and each copy, how many pipe stages you break it up into? So these are questions which essentially are microarchitectural questions. As a designer, even if you're writing RTL, you have to decide how to break up your function, right? Like that. So the thing is that if you use smaller logic depths, that means you break it up into larger number of pipe stages. That means between each pipe stage you don't have too many gates. What does that do? What it does is it reduces the idle period of a gate, because in any pipe stage, you can imagine that when the clock edge fires, it launches a wave of activity which propagates from the input of the pipe stage to the output. Right? Transitions are happening. Only when a transition happens at a gate, a transition goes past a gate, is when the gate is actually active dynamically. Every time else it's just idle, right? It's just so the idle power due to leakage, you can reduce the impact of leakage by actually having shallow pipe stages. So each one does more work. Of course, there is a counterpoint to that. The more pipe stages you put, more is the number of flops or latches you put in. So the power for flop and the area also goes up. So again, you see there is a trade-off out here, right? What is the right amount of pipelining you have to do? So this is basically, again, you see all these trade-offs, and that's kind of what a lot of engineering is to really be aware of the trade-offs and see how to answer these trade-offs by doing some analysis of the circuitry of the structure, doing some preliminary simulations, so that you can get to a answer as to, okay, this is what I should do, right? And the art of this is to actually do it reasonably accurately, but maybe not necessarily end up having to do the complete design and then come to a realization that this is how you should have done it, right? So that only will come with experiences. It's like there's no formula which you can plug in and it will tell you, okay, this is the number of pipe stages. These are things which this is the engineering you have to do. Okay, when you're designing your chip, these are some of the trade-offs which you have to kind of really work out and figure out how to do it. Now you can kind of see, coming back to the clocking style, right? You can use flop or a latch. And as we discussed in the last semester, right, you can have a latch-based design or a flop-based design. The benefit of a latch-based design is that it allows you to do time borrowing, because a latch is transparent for a small window of time, especially if you do something like a pulse latch. It's transparent for a small window of time. So what that allows you is that either the clock gets skewed, comes a little late because clock skew, or the data comes a little late. You can borrow some time from the next pipe stage. Okay. So it allows you a better management of clock skew. Now, this is what is done in high performance designs. In high performance microprocessor designs, you use shallow pipe stages, you use pulse latches and so on. So in that sense, it's the same recipe we are saying. It also is kind of nice to use it for low voltage. Except, of course, in high performance design, the clock network is different. Whereas you saw in this subthreshold, you have this shorted clock grid, right? That's what the Intel guys do. Whereas in high voltages, we don't do that, because power consumption is too much. Also, sizing which you do for high performance is different from sizing you do for low power, right? Sizing for high performance is, you know, the formula for minimum sizing, right? You have to make sure you size with equal efforts, and but that will lead you to large sizes. If you want low power and low energy, you have to keep the sizes small, but you take a hit in the delay. So there are a few places where you differ from what you do for high performance and high voltage, as opposed to what you do for low power and low voltage. So again, it's a compromise and trade-off. If you are sure that you want to target only low power, low voltage, there is not much of an issue. But if you are not sure, you have to do something which will work reasonably well. You have to again come up with a compromise solution which works reasonably well. Finally, what we have is in a design, digital design. As a designer, we never assume any gate is faulty. Okay, you write a piece of RTL or use circuit, you assume it works. If one transistor fails, you have no way of dealing with it. I mean, you just assume that it works. If it fails, you don't know what to do because you don't have any way of dealing with that problem. That is how modern design is done, except for memories. For memories, what is done is what is called ECC, error control coding, where you have extra bits in the memory, or you have extra rows and columns. So after the chip is manufactured, testing is done, and defective memory cells are identified, and those rows and columns are switched out. That means the circuitry already allows you to ignore those columns and bring in extra columns. So you have spare columns, so bring in the spare columns, defective columns are taken out, I mean they are disconnected, and you still have a working memory. So that allows you to deal with defects, hard defects. In addition, during operation, you can have errors in the memory due to soft errors, right? Alpha particle hit or some small perturbation will slip the cell. Error control coding is done so that if you have one bit failure, you can correct it, right? So you have SegDet, single error correction, double error detection. You can have double error correction, triple error detection. You can have various complexity of codes depending on how robust you want it. So that seamlessly for the designer, you don't even notice it. When you assume there's a memory, the coding takes care of it. You assume the data is correct. And you can make that assumption with very high confidence, with very high probability, it will be okay. But the same cannot be said for logic. For now, what has happened is that the foundries have done a fantastic job. The yields go up, you don't even worry. A NAND gate fails, it never happens. I mean, if a gate fails, you have to throw the chip because your circuitry is not there to take care of it. But the question is, with this sub-threshold, near-threshold computing, with so much variation, can you afford to do the design in the same way, right? Or do you also, as the design time itself, allow for failure of gates? How do you deal with that, right? Can you bring in the concepts of ECC or some coding concepts into your design? So these are things which are still in the research domain. People have been working on this for a while now, but it's not there yet, right? Mainly because there's been no need to put it in the logic, because people have figured out, the foundry, the factories have ensured that that is not required. But in the future, can we make that assumption? In the future, maybe this will become important, where you have to do designs where certain gates might not work properly, and still the whole system should work properly, right? How do you do the design in that case? So it's still a kind of interesting R&D problem, right? And remember, this has to also fit into the flow. Any digital design, any methodology has to fit into the digital flow. Is this something you can do where the RTL designer doesn't worry about it, but as a backend, the system figures out and does the redundancy? Just like what we do for testing now. Testing is something where all the circuitry for test is inserted in the backend. The designer doesn't really care about testing. They do their design. So something similar will probably have to be done. A methodology which will allow you to take a design and then make it robust by putting in redundancy and so on. Now let's look at the memory, right? And in the case of the memory, actually maybe we'll take this up in the next class because we are out of time. But before I close, any questions? on what you have seen so far?
So regarding the small slices, so we can borrow some time, but in that time the output may glitch due to unequal part delays due to SR or something. So will it not create unwanted glitches and it will not create the power consumption loop, dynamic power consumption loop?
Yes, the unequal delays leading to dynamic hazards will lead to extra power consumption. Absolutely.
So there should be transfer for the duration. In that duration, the output may or the whatever signal may switch.
Right.
For the its last rate.
Right. But just because you are doing time borrowing doesn't mean that there will be glitching, right? Those two are not, one doesn't follow the other. Your statement that yes, imbalanced delays leads to glitches, that is correct. But why should having a transparent window lead to glitching? I could have a transparent window, but maybe only one signal is the final gate which is feeding into the latch. That gate just fires a little later. So with the transparent window, you are able to still capture it.